Hello, welcome to another Research Methods for the Biosciences screencast for R. This screencast covers Section 10 T and Z tests for unmatched data and includes Section 10.1 two-sample Z test, Section 10.2 two-sample students T test, and Section 10.3 two-sample unequal variance T test. These tests are for when you want to assess if two samples are likely to come from the same statistical population or not. We often take samples from different situations, and then when we compare the data from each sample, find it to vary. The question always is whether these differences are due to random variation or whether the unique qualities of each sample situation has created this difference. Take the data from Table 10.4. Here we have measured the height of periwinkle shoals from the lower and mid-shore, and we find there is variation between these datasets. The question is, does the position of the periwinkle on the shore dictate to some extent how high a periwinkle shell will grow, or is the variation seen just due to non-perfect sampling, and if we could measure all the periwinkles on the shore, would we see no difference in the datasets? The null hypothesis would state that there is no difference between the mean shell height in millimeters of the periwinkles from the lower and mid-shore. The size of each sample is 13 individuals, and so we would use a t-test. Table 10.3 in the book, however, contains an enlarged dataset of 30 individuals per sample, and it is common practice to use a z-test on datasets of 30 or more. However, when the sample size is more than 30, then the t and z-test give very similar outcomes, and both can be used. And for this reason, most computer programs do not implement two-sample z-tests as a simple menu selection. Thus, this screencast will only cover t-tests, and you should use the test for the larger sample sizes too. One further consideration we have to make is if the variances of the samples are similar or homogeneous, also termed homoscedastic, as there are different tests for when the variances are homogeneous compared when they are not. See Chapter 10 and Box 10.1 for more details. Fortunately, the computer program will also do this analysis for us too. This is the script we are going to be using. You may wish to freeze the screencast to look at it in more detail, or alternatively, you can download it from the Resource Center. The command functions are in black, are all in lowercase, and you must enter them exactly as shown. The lines in green are notes to help your understanding of how the script flows. The words in blue are variable names and can be changed to suit your data, but you must be consistent in spelling and the use of lower and uppercase letters. And the data are in red. There are several ways to load data into R. See my screencast Introduction to R for more details. Looking at the first variable, you can see that we have used a C operator to load the data into R. So let's run the script. Track up to the beginning of the first line and click to place the cursor at the beginning of the script. You can now run the script line by line by pressing Ctrl R if you are using a Windows or Linux computer, or Command Option R if you are using a Mac. We're going to start by defining the variables using the C operator. My first variable is lower shore and my second variable is mid-shore. I now have both my samples entered. The first thing that I have to do is to test the variances to see if they're homogeneous or not. Here I'm going to use the test var.test. We can see it gives us a p-value of 0.07787. So what is the meaning of the p-value? A p-value of 1 means we can accept the null hypothesis as true, whereas a p-value of 0 means we can accept the null hypothesis as untrue. As we travel from a p-value of 1 to 0, the transition point between true and untrue is set at 0.05 in the biological sciences. The smaller the p-value below 0.05, the more confident we can be in rejecting the null hypothesis. So a p-value of 0.07787 is above our transition value of 0.05, which means the result is not significant and that we cannot reject the null hypothesis that states there is no difference between the variance of periwinkle shells from the lower and mid shores. It tells us that we have to use a t-test for equal variances. So let's do the t-test. If I scroll down, you can see I've given you the command to perform the test for samples with both equal and unequal variances. The test instruction is t.test and is the same for each, but it is the var.equal attribute which can be set to either true or false that determines which test is done. We want the second option, so I'm going to track along and click to put the cursor at the beginning of the second option and then run the line. We can see that it has given us a p-value of 0.3972. which is above our 0.05 transition value, indicating a non-significant result and that we cannot reject the null hypothesis that there is no difference between the height of periwinkle shells from the lower and mid shores of Porthcawl in 2002. I hope you found this screencast helpful. For further information on how to use this test, or the theory behind it, then please consult the book. More information on how to use the program to perform the test can be found in our online web guides located in the Resource Centre. Thank you for listening.